All right, so as you guys mentioned correctly, there are 4 colligative properties, so that's a good short answer question on the exam. So now we'll go into the equations. So I will give you the equations on the exam. Okay, I have to tell you this, and it kind of messed up my day, but somebody wrote on me, said that there's so much stuff and there's too many equations to memorize. Complaint on me. I get a lot of complaints. And I'm thinking to myself, and I can't. I'm giving you all the equations. I swear. Yeah, the equations are on the exam, and if I mess up the equation, I take it back. But no, there's too many equations to memorize. So here's the equation for vapor pressure lowering. Okay, so no memorization. Okay, so the vapor pressure of the solution, which is solute solvent, is going to be this. Okay, I'll give you this on the exam. Okay, vapor pressure. It's the pressure exerted by a vapor. Okay, it's going to equal to this cursive X of the solvent. Okay, this cursive X means mole fraction. Mole fraction. Okay, times the vapor pressure of the solvent neat. Okay, what do I mean by neat? Neat means by itself. Vapor pressure of the solvent by itself. We call that neat. Neat, like neat dichloromethane, or neat ethanol, or neat hexafluoroisopropanol. Neat just means by itself. That's just the lingo. Okay, so I'll give you this on the test. So this cursive X solvent is mole fraction of the solvent. Okay, solution is solute plus solvent. Okay, so this is the moles of the solvent. Divided by moles of solvent plus moles of solute. Oh, I think I skipped a page. Okay, anyways, let me give you the equations and then we'll go back to page 4. Okay, I just realized I skipped a page.
Is that plus? Solid?
Yes, plus. Okay, so that's mole fraction of the solvent. Okay, and this is the vapor pressure of the solvent alone. Okay, this will be given also. Vapor pressure of the solvent alone. Right, so this is one equation for this vapor pressure lowering. Okay, I'll give you that on the exam. Okay, the second equation for boiling point elevation is going to be the new boiling point, delta TB, is going to be KB times molality. Molality. Okay, so KB is another constant. Okay, we're going to call that the boiling point molal constant. So it's going to be for different solvents. It will have a different constant. Okay. And then the freezing point depression. So I'll give you that on the exam, and I'll give you the constants as well. Okay, the new freezing point will be K of F, which is the freezing point molal constant. As I said before, all constants will be given. So you'll be given F, you'll be K of F. If you want to calculate the new freezing point, once you add a solute to a solvent, you'll be given the Kb once you add the solute to the solvent, because Kb for water is different as a solvent than would be different than ethanol as the solvent, or benzene as the solvent, or cyclohexane as the solvent. And then M, as we know, is molality. Okay, so I'll give you those equations along with the constant. And then for osmotic pressure, osmotic pressure is pi, and this is molarity times R, which is the gas constant, times T. Okay, so these are the 4 equations for each of the 4 colligative properties. I'll give you them along with the constants. Okay, here R is the gas constant, and I'll give you that constant. Okay, so basically it's plug and chug, plug and play. And then T is the temperature here. All right. So as far as examination is concerned, you just need to know how to plug and play these 4 equations. Okay, I'll give you the constants. This little cursive x, go back to the first equation. This cursive x is called the mole fraction. Okay, so this one here, boiling point elevation and freezing point depression. Okay, if you add a solute to a solvent, what will be the new boiling point? Be higher. Okay, so what will this change be? Will you add or subtract if your boiling point is going to be higher? You're going to add delta TB, because why? It's boiling point depression, it's boiling point elevation, so the change will make it the new boiling point higher. Okay, what about delta TF? You get the change, you calculate the change in the freezing point. What will you do? What will the new freezing point be? It'll be what? Be lower. So you're going to take this, and the new freezing point will be lower. So you subtract delta TF to get the new freezing point. So these are the 4 equations. We'll go over them, but I just realized that we did not go over page 4. Okay, so let's go back to page 4. We will skip 5 and 6, as I mentioned to you guys before, and let's finish up some practice problems on page 4. Sorry about that. I forgot about page 4. I'll give you this answer later. Okay, so you can work at this at home and use it as practice, and I'll give you the answer and post it on Canvas. Okay? For now, we'll do this problem and this problem. All right, so coming back to page 4 of our notes here. All right, let's do our quick recap for the exam. A good short answer question, units. So what is the units of molality? Let's see if we can have this memorized.
Moles of solute.
Correct.
Over kilograms of solvent. Or solvent.
Kilograms of what?
Solvent.
Yes. Okay, moles of solute over kilograms of solvent. Okay. So in this problem here, we want to calculate molality, which is lowercase m, and we have a molarity, which is big M, also called molar. And so for an exam, short answer, what would be the units of molarity? I think we went over this. Moles of solute over what? Liters of solution. Okay. Right, so here in these types of problems, we have to convert from one to the other. Okay. So here's how we'll convert from one to the other. Okay, 5.86 molar is nothing more than 5.86 moles of ethanol. over liters of solution. Okay, we can assume that our solvent is going to be water. Okay, we can assume that our solvent is going to be water. Okay, we'll assume our solvent is water. If our solvent is water, what is our solute? What's our solute? Okay, solute is ethanol. Okay, our solute is ethanol. All right, our solute is ethanol. So we want the molality. So our molality is moles of solute over kilogram of solvent. So we have our, what's our solute again? Ethanol. And what is our solvent? Okay, water. Okay. So we want molarity. So moles of solute, we got our moles of solute. We want molality. So kilograms of solvent. Kilograms of solvent is what we need. Okay. So 1 liter is how many milliliters? Okay, 1 liter is 1,000 milliliters. Okay, of solution. Okay, it's the same thing. 1 liter is 1,000 milliliters. And one thing that we do know is that's given to us in this problem is the density. Okay, which is 0.927 grams per mil. Okay, so we're going to take this density in 1,000 mils of solution, and we're going to get the grams of solution. Okay, we're going to take this, which is the same thing as 1 liter, 1,000 mils, and we're going to get the grams of solution. Okay. So we have 1,000 mils. Okay, let's multiply it by the density given to us in the problem. So this comes about to 927 grams of solution. All right. And another thing that we know is that the grams of solution equals grams of solute. Grams of solution is equal to grams of solute plus solvent. So what is our grams of solution? Okay, it's 927 grams. What is our grams of solute? Let's go ahead and convert this to grams. Okay, let's go ahead and convert this to grams, the moles of ethanol. Okay, we'll do that in red ink. So 5.86 moles of ethanol times 1 mole of ethanol. How many grams is in 1 mole of ethanol? So carbon is about 12.01. Okay, carbon is about 12.01. Okay, hydrogen is about 1.01, but there's 3 units. Plus another carbon is another 12.01. Okay, plus another 2 units of hydrogen. Hydrogen is about 1.01 times 2. Plus oxygen is about 16, right? So 16.01. Do you remember these numbers? Okay, you get them from the periodic table. So, okay, plus hydrogen is another 1.01, 46.09. So I'll have periodic tables out, but if you have a periodic table, from home, you can bring that, but I just know carbon, hydrogen, and oxygen. All right, so the moles cancel. So 46.09 times 5.86 is 270, we'll just call it 271 grams. Okay, 271 grams. Okay, plus grams of solvent. Plus grams of solvent. Okay. So how will we get our grams of solvent? How will we get that? What will we need to do? It's going to be, grams of solvent is going to be 927 minus 271. Is that correct? So what's 927 minus 271? 656 grams of solvent. Very good, thank you. All right, let's convert that to kilograms of solvent. What is that in kilograms? That's 0.656 kilograms. Okay, you take the decimal and move it 3 to the left, so that's 0.656 kilograms. And I think we are all set to solve this. All right, so this is going to equal to moles of solute, which is 5.86. Kilograms of solvent, which we can assume is water, is 0.656. And what's 5.86 divided by 0.656? Do you have that, Antoinette? Want to check that with me? Divided by 0.656. 8.9 lowercase m. Okay, so as long as I did my calculations correct, I'm getting an answer of, as long as I did the calculations in the calculator correctly, I'm getting about 8.9 lowercase m. Let's do 8.93 because they have 3 sig figs here, so 8.93. Molal. Okay, lowercase m. All right. So on Tuesday we went from I think we did the opposite on Tuesday. We went from molar to molal, and here we went from molal to molar. So we did so here we went from here to here, and then on Tuesday we went the opposite way. Okay, we went from there to there, the conversion. Okay, we used density to help us as the intermediary. All right, let's do one more problem here. Calculate the molality. Okay, so what do we know about molality? What are its units? That's correct. Moles of solute over kilograms of solvent. It's 44.6 mass percent aqueous. Okay, so here the solvent is clear to us. What is the solvent? Aqueous, which means what is it? Okay, water. Okay, aqueous, aqua, water, right? And what is our solute then? Okay, our solute is going to be NaCl, sodium chloride. All right, so we need to calculate the molality, which is moles of solute over kilogram of solvent. And so 44.6% by mass, okay? So this means 44.6 grams of sodium chloride by mass divided by 44.6 grams of sodium chloride plus how much water? It's a percentage, okay? So by how much water? So how much is your test worth? 55.4, okay? So 55.4 is 100, okay? 100 grams. So our solvent is going to be 55.4 grams of water. Okay, 55.4 is the same thing as how many kilograms? Okay, we're going to take the decimal and move it 3 to the left, correct? So, Jacob, right? It's going to be 0.0554. I'm just moving the decimal 3 to the left. 0.0554 kilograms. Okay, nice. Very good. Okay, which is our solvent, which is water. And the moles of NaCl, let's take these grams and convert it to moles. Okay, 1 mole of NaCl contains how many grams? Here you probably do need your periodic table, but sodium is about 23.01. And chlorine is about 35.45, I believe. Okay, and about 58.46 grams, okay, in 1 mole of sodium chloride. .46 divided by 58.46 will give us moles. 58.46. 0.763 moles of sodium chloride. Alright, so molality is moles of solute over kilograms of solvent. So moles of solute here is 0.763 moles. The kilograms of solvent is 0.0554 kilograms. And I think if I did my calculations and everything correct, this should be the answer of about 13.8. Yeah, let's do 13.8 lowercase m for molal. So just to save time, you can do this at home, and I'll post the answer on Canvas. So that's page 4. Okay, like I said before, page 5 we will skip. Okay, so page 5 it gets skipped. Page 6 gets skipped. And then let's move on to page 7. so we'll do a problem involving vapor pressure lowering. These are 4 colligative properties. Okay, so we'll do a plug and play problem, and that's going to be on page 7. Okay. So calculate the vapor pressure of a solution made by dissolving 82.4 grams of urea, which has a molar mass of 60.06 grams per mole, and 212 mils of water. The temperature is 45 degrees. So vapor pressure is always quoted at a specific temperature. Okay. So what is the vapor pressure lowering? So let's draw this out. Okay, let's draw a picture here. Okay, so we got 212 mils of water. Okay, and what's the temperature? 45 degrees. Okay, and what is the vapor pressure of water at 45 degrees? Okay, the vapor pressure at water at 45 degrees is 71.88 millimeters of mercury. Okay, so that's something we get from the table. You don't have to memorize, because remember, vapor pressure is quoted at a specific temperature. Okay, you change the temperature, you change the vapor pressure. 71.88 millimeters of mercury. Okay, this is by itself, or neat water. And then to that 212 milliliters, okay, we're still at 45 degrees. Okay, we're adding 82.4 grams of urea. Okay, so question for us is, what is the new vapor pressure? So this is what we're trying to find here. Okay, so the equation, which I'll give you on the exam, is the new vapor pressure of the solution is going to equal to the mole. This little cursive X is the mole fraction of the solvent times the solvent by itself. All right, here's a question for the class. What is the solute and what is the solvent in this situation? The solvent is, this should be the easiest question in all of the class. What's the solvent? Okay, water. Okay, water's, they call it the universal solvent, but yes, the solvent is water. Okay, I put D for distilled. Normally in the lab we don't put tap water. Okay, maybe we want to put some clean filtered water, so that's the D. Okay, but it's water. And then what's the solute then? Okay, urea is the solute. Okay, urea. Well, powdered urea. All right, so I'm going to do it using this equation, but I'm also going to do it another way, using another equation, just to illustrate you a point. We can also do, not just calculate the vapor pressure straight up, but we can calculate by how much the vapor pressure has lowered. That's the delta P solution. And in this case, it's going to be the mole fraction of the solute times the vapor pressure of the solvent by itself, neat. Okay, so these are an alternative equation here. Okay, but this gives you the change by how much it has lowered by. Okay, so this one I'll give you on the exam. Okay. So now let's just plug and play. Okay, this is what we want to find, the solution, because we added our solute to our solvent. Right, so the moles of the solvent is water, 212 milliliters of water. Okay, so the density of water is about 1 gram per mil. Okay. That's just the back of the back of the mind density. Okay, so the density of the water is 1 gram per mil. Okay, this is the density of water. And then 1 mole of water is about 18.04 grams of water. Alright, so the mils and mils cancel, the grams cancel. Okay, so 1 gram per mil, if you can memorize that, that would be good as just the density of water. It's going to be about 1. And this is what we need to calculate the moles of water. And 212 divided by 18.04. About 11.75, I'll add some extra digits here, 11.752 moles of water. Okay, remember this is our solvent. Okay. And what is our moles of solute? So this will be moles of solvent. Okay, moles of solute. Let's go ahead and calculate that. It's urea, and let's do it in green. Let's just keep it in this color. So we have 82.4 grams. Let's do it in green. Okay, so we have 82.4 grams of urea times 1 mole of urea is about 60.06 grams of urea. So 82.4 divided by 60.06. About 1.372 moles. Okay, 1.372 moles of our solute. Alright, so what is our definition of mole fraction? Okay, can anyone tell me? It's a fraction. Okay, so we'll do the mole fraction of the solvent. So it's a fraction. What always goes at the bottom of the fraction? It's going to be the whole thing. What's the whole thing? Correct. So this is going to be 11.752 moles plus 1.372 moles of our solute. Okay, here in the denominator it's going to be the solvent, which is 11.752 moles. Okay, let's go ahead and do the same thing for the solute. Okay. What would be the mole fraction for the solute? Okay, what always goes at the bottom? Solute plus solvent. Okay, but here, what goes in the numerator? Okay. One is the fraction of the solvent over the whole thing. Our solvent is going to be water. The other one is the fraction of the solute over the whole thing. Here, our solute is urea. So I just thought we'll just calculate both. All right, let's first do this mole fraction of the solvent, moles of solvent over the total moles. So this is going to be 11.752 divided by parentheses 11.752 plus 1.372. I'm getting about 0.895. I'll add an extra digit here, 0.895. Okay. And then let's just for kicks, let's calculate the mole fraction of the solute. Divided by the sum of this. I'm getting about 0.1045. Okay, I just carry an extra digit there. All right, let's plug in our equations here. So this is the equation that I'll give you for the test, but I just want to show you that you can also use this equation. So the mole fraction of the solvent is going to be 0.8955. Okay. And what is the vapor pressure of the solvent alone? 71.88 millimeters of mercury. Okay, 71.88 millimeters of mercury. And what is this on our calculator? .8955. .4 millimeters of mercury. So it went down from 71.88 to 64.37. This is our answer. And it lowered. Okay, that's what we expected. Okay, 64.37.
So wait, was the table that has the temperatures and like the water and all, was that to provide for like?
Yes, you don't have to memorize that table. Yeah. We don't memorize things, okay, unless, I think it's important enough to memorize. All right, so this is the answer. It went down. Okay. And what is one of the colligative properties in terms of vapor pressure? One of the colligative properties is that it should go down. All right, let's utilize this equation here, okay, just for fun. All right, let's utilize this equation. Here. All right, so this is the mole fraction of the solute, which is 0.1045 times the solvent by itself. The solvent by itself is 71.88 millimeters of mercury. Okay, so this is the change. And what's 0.1045 times 71.88? 0.1045 times 71.88. I'm getting about 7.51. 7.51. I'll put in extra digits here. We'll just go 7.51 millimeters of mercury. Okay, so this is how much it gets lowered by. Remember, vapor pressure lowering. Vapor pressure lowering.
So what's the difference between the P salt solution and the delta P solution?
This gets lowered by 7.51 millimeters of mercury.
Okay, and then the first one is that, and the other one, the 64, that's how much that one gets lowered by?
Yeah. So when you're calculating delta P now, you're going to take the 71.88. It's vapor pressure lowering. So what will you subtract? 7.51. So we're going to take 71.88 millimeters of mercury minus the delta P. And what is this on our calculator? 64.37. And we're right on the dot. Okay. So depending on which equation you use, you'll get the vapor pressure of the solution straight up, or the change by how much it goes down by. Okay, by how much it goes down by. Because remember, the colligative property is that vapor pressure goes down. All right, so yeah, on the exam, in terms of examination, you're going to get this equation, but I just wanted to show you this equation, and it's just plug and play. Okay, plug it in and chug it out. Okay. All right, let's move on. Our last, how much do we have? Last 15 minutes or so. All right, let's do one more vapor pressure problem. This involves organics. You guys know what organics are? I mean, how many of you are going to take orgo or organic chemistry? Okay, all the PA students, all the medical students have to take organic chemistry. So here, organics have to do with, how do you say it, combustibles. Okay. Or flammables, maybe. So the MEOH stands for methanol. The ETOH stands for ethanol. And what states are these? Okay, remember in the lab? Okay, methanol is a liquid. What about ethanol? It's a liquid. So these are two liquids. Okay, in our previous problem, water is a liquid, urea is going to be like a white powder. Okay, solute. Here we're having two liquids, two solvents essentially. Okay, the methanol solvent and the ethanol solvent. Methanol has its own vapor pressure. Ethanol has its own vapor pressure. Okay, what functional group are these called? Just as a review, methanol and ethanol. Okay, these are the functional groups known as the alcohols. Very good. Okay, so here we have two liquids, and the mole fraction of one of them is 0.576 at 25 degrees. So remember, vapor pressure is quoted at a specific temperature. And at 25 degrees, the vapor pressure of methanol by itself is 127 millimeters of mercury. So we have the mole fraction here of methanol. And then at 25 degrees, the vapor pressure of ethanol is 58.6 millimeters of mercury. So what are they asking for? Oh, yeah, they're asking for the vapor pressure of this solution. Okay. All right, so let me draw it out for you guys so it makes more sense. Okay, so here we have methanol by itself. Okay, neat methanol. Okay, we have ethanol by itself. And we have a combo of methanol and ethanol. So methanol by itself has a vapor pressure of 0.576 at 25 degrees. I'm sorry, no. I'm so sorry. Methanol by itself has a vapor pressure of 127 millimeters of mercury at 25 degrees C. Okay, that is its vapor pressure. Ethanol has a vapor pressure at 25 degrees C of 58.6 millimeters of mercury. Okay, now we want to calculate in this problem what is the vapor pressure of when we join them together, where the mole fraction of methanol is 0.576. Okay, mole fraction. Okay, so we want to figure out the vapor pressure of this, okay, combo, okay, when we join them together. Okay. All right, so just as a review, we have a vapor pressure of methanol neat, which is 127 millimeters of mercury at 25 degrees. We have a vapor pressure of ethanol neat by itself, which is 58.6 millimeters of mercury at 25 degrees. Okay, we're going to mix these two liquids together, methanol and ethanol. The mole fraction of the methanol is 0.576, okay, in this solution, in this combo, okay, in this mixture. So if the mole fraction of methanol is 0.576, we can automatically calculate the mole fraction of ethanol. What will that be? Okay, this cursive X is mole fraction. What would be the mole fraction of ethanol? It would be, what's the total here? 1. So what's the mole fraction of ethanol if the mole fraction of methanol in the problem is 0.576? What's 1 minus 0.576? 0.424. Right. Okay. We got that because if the mole fraction of methanol is 0.576, then automatically the mole fraction of ethanol in this methanol-ethanol solution has to be 0.424. Okay, they have to add up to 1. Okay, so now we have this mixture with the corresponding mole fractions. Here what we do is we add them together. This is like Dalton's law of partial pressure. Okay, Dalton's law of vapor pressure. So we're not going to use that equation. We're going to use this equation, okay, because we can add them. Okay, why can we add them? Because these are two liquids, number one. Okay, it's not like a powder in a liquid. Okay, it's not like a powder. It's not like a powder in here. Okay, they're two liquids. And the number two is that these are flammables. Okay. All right, so we will add them together, okay, because they're two solvents. So we're going to take the 0.576 and and multiply it by the vapor pressure of methanol alone, which is 127 millimeters of mercury. Okay, plus the 0.424. Which is the ethanol, and what is ethanol? 58.6 millimeters of mercury. Okay, and we can add them up like this because it's two liquids. Okay, remember in the lab, okay, you did methanol, you did the evaporation, then you did the evaporation of ethanol. In this problem, we join them together in this mole fraction and at that mole fraction. All right, so 0.576 times 127, what is that on our calculator? Okay, plus, so that's 73.15. That's the vapor pressure contributed by the this one here, the methanol, plus, let's do this one, (24.84 millimeters of mercury). Or 24.85. And because they're two liquids, it's not a solid dissolving, it's not particulate into water, it's two solvents. We'll add them up to get the total vapor pressure. And what is this on our calculator? (24.85 plus 73.15, 98. Okay, 98.0 is total. Just do 98.00. Okay. All right, this is our answer. All right, two solvents. Methanol has its own vapor pressure, ethanol has its own vapor pressure. We join them together, this is the new vapor pressure. Okay? We dissolve urea. It's kind of like a sugar, it's like a, well, it's not sugar, but it's kind of like it. We dissolve urea, or white powder, into liquid water. We utilize this equation. Okay? That's the difference in the vapor pressure calculations. All right, let's check the time here. Let's see if I can squeeze in one more problem here.
It's 10:39.
Okay, we'll just right, so let me tell you what we will do on Tuesday. Tuesday we'll just continue doing more of these practice problems. I will probably 10, 11, 12, 13, 15. Okay, so we'll go up to page 15. Okay, we'll go up to page 15, and then pages 16 onwards is just for your own independent study. Okay, but that will not be on the test. Okay, we'll go up to page 15. We'll try to finish that on Tuesday, and then Thursday I'd like to have like a test review, or we'll do a practice test together. Right, and don't forget the lab. Okay, the lab I will not test you on. I'm not going to lecture on it because it's on solids and we don't have time to talk about the science behind solids. Okay, they have a density and you'll calculate all the unit cell dimensions for Tuesday or Monday, whichever lab you're in. All right, have a good weekend. Turn in your homework. By the way, you can check your answers to your homework. The instruction manual is on Canvas. That's another thing. Okay, the answers are, it's an honor system. Check the answers on Canvas. Okay, and then upload it. I'll give you 10 points.